Okay, so our next speaker is Judy Hoffman from Georgia Tech. Judy Hoffman, her research lies at the intersection of computer vision and machine learning, with a specialization in domain adaptation, transfer learning, and adversarial robustness and algorithm fairness. She received her PhD in ECS from UC Berkeley in 2016, after which she completed a postdoc at Stanford University and UC Berkeley. Judy, the floor is yours. You can share your screen.
Great, thank you. All right, thanks to the organizers for inviting me to speak today. And I'm excited to be here and talk to you a little bit about some recent work that has to do with detecting reliable instances for learning. And to get started, I just want to briefly talk about the standard supervised learning setup. Let's get ourselves acclimated with this setting and try to understand why it is that we might need to be able to determine something about particular instances and their reliability when we're going about the learning. So the standard protocol involves, of course, collecting some large data set. And then when you're training in a supervised fashion, you're going to have labels for this data that were collected by human annotators. And at training time, you're going to randomly sample throughout every mini batch some collection of images together with their labels and use that to train with a supervised loss. So what are some of the potential downsides of just using this random sampling type approach where you treat every instance essentially equally, and you're going to have the same likelihood of viewing it, the same amount of time is going to have the same impact on the learning process? Well, the first potential downfall is that sometimes throughout the labeling process, you may have incorrectly labeled instances. Now, this could be because of benign causes, an annotator made a mistake, maybe, or it could be because of malicious cause, like in Tom's talk right before this, maybe an annotator explicitly tried to provide an incorrect label, or maybe they provide a manipulation here that to the image itself that would impact the training process. It could also happen when you're using semi-supervised learning protocols where the label is not necessarily curated by a human annotator, and instead it's been inferred through using an auxiliary model. Another way in which your data can cause you some problems is if the image itself has been manipulated. So maybe the label is correct, but your model has a difficult time being able to predict the label that you'd like it to predict at the end of the day. And then finally, there's just always going to be circumstances where an example is difficult to learn or inherently ambiguous, like this example of a dog that also has many features that are reminiscent of a cat. And of course, there's lots of different literature studying these types of problems and ways in which we can explicitly try to account for these potential data pitfalls throughout our learning process. And we heard about a lot of them today, especially in the adversarial robustness space, and I'll talk about that a little bit in today's talk. But there's also, of course, curriculum learning for trying to understand some of the easier samples first before we move on to the more ambiguous samples. And then, of course, there's learning if you know that there may be some label noise. So at the end of the day, because you're going to have data of variable degrees of trustworthiness, we'd like to be able to make sure that when we're learning with our data, we have some sense of reliability, both in terms of the model outputs, but also in terms of the data that we use as input to the model training. And of course, I think a speaker earlier today already mentioned that this slide is probably going to be shown over and over and over again. You have these instances where we have images that have maybe been manipulated, potentially in imperceptible ways, and they cause dramatically different predictive outputs. And this is really why people are so focused on this, is because it's concerning that they're imperceptible to people, but they can result in such different outputs from our learned models. So this kind of implies to us that there are some fundamental limitations of our models and certainly some vulnerabilities. So if we are trying to be able to understand which images we might want to rely on more for training, perhaps some of these vulnerabilities that are illuminated through the adversarial examples can actually provide us some pieces of information. And to start to understand that, let's first start to think about what an adversarial example does. So let's imagine we're taking this MNIST example of a 0. And just for visualization purposes and to gain some intuition, let's just take this tiny image, vectorize it, and map it into a 2D projection space so that we can use visualization. And for this particular example, we're using just a random 2D orthonormal basis, but you could imagine using other projections, especially projections where a particular direction is found through an adversarial approach. Once we've projected into this 2D space, we can now imagine applying different, in this case, random perturbations using a grid-like search over this 2D space. And each of these grid-like points is going to correspond to another image. Here's one example output image here of a different 0. And we can imagine taking all of these perturbed images and passing them through the same trained model. The reason we want to do this is we want to gain some understanding of what would the model's behavior be as we manipulate an image in a particular way. Now, in this case, it's again a random manipulation, but you could do this for any image across directions that were learned using some sort of gradient or signed gradient method. Well, once we do that for this image, we're going to get a decision landscape output that looks like this. Now, the training data point is shown in the center, and you can see that, I mean, this is an MNIST classifier. These work really well out of the box, so it's correctly classifying this 0 as a 0. But what's interesting to note is that if you move in a particular direction here with a particular step size, you can start to change the output of the model. And overall, this is not necessarily going to be the same amount or same magnitude of movement that you need to walk in all directions. So there are some directions that are more vulnerable than others. But the takeaway is that it's a fairly small perturbation that's needed in order to start changing the outputs of the model itself. And we know in this workshop, we're talking a lot about adversarial examples, and this is exactly the sort of phenomenon that's exploited in order to create those examples, is by finding the direction that you need to walk the least amount in order to be able to start changing the output of the model. Now, in order to defend against this, and I know Tom talked about this in just the last talk, I'm sure people talked about it in the morning session as well, a really common technique is to just say, well, let's make sure at the end of the day, my model is reporting the correct label that I would like it to label on this output image. So adversarial training is just really augmenting your data set with these adversarial examples. So adding a new point from that decision boundary, which previously was misclassified, and making sure that the model kind of increases its margin around that particular sample. And this should increase the reliability of that sample and make it more robust against that particular style of adversarial attack. Now, this is something that you can do when you have access to labels. But another question you could ask is, aside from training with all of these adversarial images, using this kind of augmented training procedure, we can also just think about asking the question of how vulnerable is a particular image by thinking about whether or not manipulations to that image with a particular step size, particular epsilon vol, is going to result in a correct output prediction or a manipulation to that correct output prediction. So in standard robustness metrics, what we're going to do is we would normally look at the data set in aggregate, and we would think about how robust is my model against a whole collection of images. But an equally valid question to ask is how vulnerable is a particular image to being manipulated in this way? And once you start thinking about that, you realize that you can leverage the fact that there's a spectrum of instances, some that are less vulnerable and some that are more vulnerable. And you can explicitly use that information either to improve your learning procedure or to gain some insights into how your model performs overall. And so in this work that was led by Yogesh Balaji, and it was also joint work with Tom from the last session, we thought about this problem of having an instance adaptive adversarial training. So in the case of this work, what we were trying to do was just understand how vulnerable each particular instance is and see whether or not we could change the amount of perturbations that were applied to each instance during learning so that we could avoid having drops in clean accuracy in order to have the desirable robustness benefits that you get from adversarial training. But for the purpose of this talk, the key piece that I want to point out is just that when you are thinking about the reliability of particular instances, one way in which you could measure this is you could think about how much that image needs to be perturbed before you start misclassifying it. So here's an example where we have both an instance on the left here, which doesn't need to be perturbed very much before it starts to be misclassified, and an image on the right that needs to be perturbed really more significantly than even is usually done inside adversarial training with an epsilon of 28 before it starts to be misclassified. So this gives us some sort of a curriculum or a sense of how canonical, how easy to manipulate a particular image is. And so this might be able to be leveraged either directly, as it was in this work, to incorporate different amounts of robustness for different instances, or to create an implicit curriculum that tells us which instances are perhaps more canonical and more closer to the mode of the distribution for a particular category of interest. So in this work, we changed the standard adversarial training procedure, and instead of applying a fixed epsilon parameter to every instance, we had an instance adaptive epsilon parameter. That was derived in a very simple search procedure. By doing that, we were able to find a set of samples that could be manipulated. This was in the CIFAR data set with really small epsilons. So these are going to be samples in this case that were kind of ambiguous to begin with, and perhaps we don't want to devote a lot of our effort during robustness training to making sure that you're robust against those types of samples. And maybe it's more important that we focus a lot of effort on making sure that you do not, that you're not lacking robustness on these canonical samples on the right here. And by doing this, we're able to produce an algorithm that can produce a single model that was outperforming adversarial training with a fixed epsilon ball, both in terms of the combination of natural accuracy and adversarial accuracy. So for this work, we were really just thinking about how can you use different perturbation, different strengths of perturbation, and different measures of robustness for across your instances as a way to have a more flexible training procedure that doesn't over prioritize robustness over just model performance in general. But this was all in the supervised learning context, and this was again focused pretty heavily on pure robustness. But you can actually have degraded model performance pretty substantially due to variance in your data when you're talking about semi-supervised learning. So even before you have an adversary in the mix, just through the learning procedure, when we think about how semi-supervised learning works, we of course have some amount of labeled data that you can train with a supervised loss and get strong generalization performance as a result. But aside from that, you have potentially a larger amount of unlabeled data, and you need to be able to learn with an unsupervised loss. And quite frequently, the way that these models are learned is that they're going to leverage the current model's best output guesses on these unlabeled data by generating what we'll call pseudo labels. and then training a model using either an explicit pseudo-label loss or potentially something like an entropy minimization loss. But what this means is that any vulnerabilities that the model has, and it may potentially have many more vulnerabilities than the standard models that we'll look at in adversarial robustness, are going to be exploitable by this unlabeled data. And sometimes if we're thinking about the adversarial training, the standard idea is that we're going to explicitly use the label that was available from your clean image for training with your adversarial image. But if you don't know what label, because this is unlabeled data in general, then a common procedure that people would use is called virtual adversarial training, where what you first do is you predict on your clean instance and take the output prediction as the ground truth target and use that for your adversarial training. That seems like an intuitive algorithm because you're basically just saying that what I want to do is make sure that the model continues reporting whatever it was already reporting on my clean data. I don't want it to change that on my adversarially perturbed data. And so it's kind of still adding some robustness around the current prediction. But the problem, of course, is what happens when the clean prediction is wrong itself. Well, now you're going to be incorporating some sort of robustness and padding around an incorrect pseudo label. So we need some way to understand whether or not we can rely on the current labeling, the clean labeling of the model itself. And this problem is exacerbated when we start to think about a semi-supervised learning problem where the labeled data and unlabeled data may not be drawn from the same distribution. So this is what we see in unsupervised domain adaptation, where the standard setup assumes that you have a labeled source data set, and this data is going to be drawn from some imaging distribution. In this case, it's going to be the sketch domain. And then you have a large unlabeled data set that you would like to deploy your model on. And the key idea is that you'd like to be able to leverage information from the source data set for use in the target domain, even though you don't have access to labels in the target. And people have looked at using virtual adversarial training as a way to encode some amount of adaptive performance benefits. This one method called DIRT-T or VADA was really the key underlying piece of the model that used the virtual adversarial training, looked at both an alignment mechanism using a standard domain divergence or aligning distribution outputs, but it also used a virtual adversarial training. And the way that it used it was it assumed that you had a source model. So again, a source model in this case could have been trained on this domain up here, maybe a sketch domain or more generally just some domain where you had access to lots of labels. And then what would happen is they would look at the output prediction from that source supervised trained model as it's applied to these unlabeled images here. And they would assume that's my clean prediction, whatever the source predicted on this unlabeled target instance. And I want to now train with an adversarial perturbation, an adversarial loss, to be able to make sure that I am updating my model to predict the same output that I had from the clean and from the adversarially perturbed. And it worked decently well, but of course, it's going to be highly susceptible to the same problem of what happens if that original clean label was incorrect. And to give you an example of how this might happen more broadly, just simple example for semi-supervised learning, why would my original labeling sample be incorrect? If I have two classes here, circles and triangles, if everything is labeled, I can learn a decision boundary that classifies everything correctly. But if I have only the filled in points labeled, I might learn a different classifier that would, in particular, if I use the current predictions as my clean predictions, either through a pseudo label loss or through a virtual adversarial training loss, I would now have some samples that are incorrectly labeled. And if the goal of my semi-supervised learning approach is to say that the current prediction should be amplified I'm going to result in a situation known as error accumulation. I'm going to be updating my model parameters to make sure that whatever prediction I had now just has an even stronger buffer, but same labeled output. And this is a problem, and it's hard to recover from, and sometimes can lead to models that are trained in this semi-supervised fashion completely diverging. And when we're talking about a domain adaptation setting where my original labeled data set is drawn from a different distribution than the target, then this initial model that I learned on my labeled data is very likely to be misaligned with the unlabeled target instances. And so any poor initialization, which by definition, because they are drawn from different distributions and because we want to adapt it for more effective use, is going to be the case, then the initial labelings that you find from the source model on the target instances are going to have a high likelihood of being incorrect. And so we're going to be really stuck in this situation where if we use any supervised learning objective, entropy minimization, pseudo-label loss, or virtual adversarial training, any of them are going to have this challenge where the instances that are currently labeled incorrectly are going to, those errors are going to be reinforced, and we're going to just accumulate them more and more over time. And so we'll result in this situation where we pull all of our instances, especially with entropy minimization, we pull all of our instances closer to the cluster means, but we're not necessarily resolving any incorrectly labeled instances. So what can we do about this? How can we make sure that we can leverage some of these robust training procedures and training procedures that can really be used in a semi-supervised context, but without hurting our performance by over-trusting every instance? We want to instead only trust the instances that we deem to be more reliable. So there's been a lot of work in this space. I'm going to mention a couple of different things, but one big area where people have looked at trying to understand whether or not an instance is reliable is in trying to detect something about errors in the model. And one such work that I'm highlighting here from 2019 used really simple procedures where they just applied standard off-the-shelf simple image transformations and asked how much did the model change as a result of applying those transformations. You could imagine doing something really similar with adversarial perturbations, just asking, same thing as in that instance adaptive adversarial work where we ask the question of which examples do we think are more reliable, more canonical, by seeing how much of an epsilon ball I can perturb the image before it starts to change its classification. But you can do the same thing with other types of transformations to the images as well, and that's been shown to be effective both at detecting adversarial examples as well as somewhat less effective but still reliable at detecting natural image errors. And this key insight about looking at different transformed images and trying to make sure that a model is invariant to these different transformations, of course, with the adversarial perturbations has been leveraged through adversarial training and virtual adversarial training, but also in standard unsupervised learning, it's been leveraged in the contrastive learning framework to popular methods, SimClear and MoCo, use these different image augmentations and ask for learning invariance during training. So we wanted to see whether or not we could use some of these image augmentations as a way to detect reliability of instances before we use them for our semi-supervised training. And in this work, SENTRY, that's what we did. The key idea is that we're going to try to derive a predictive consistency measure, and that will be used in order to overcome the fact that the original output model's confidence scores, especially when you're dealing with a domain adaptive setting where the initial model is trained on a different distribution than your test distribution, those scores tend to be miscalibrated and can't be used out of the box necessarily. And then we'd like to be able to use some sort of semi-supervised learning where we're going to increase the model's confidence, but only increase it on the target instances that are deemed to be reliable. So briefly, the way that the model works is that we start by learning a supervised model on our labeled data. We then train a model on our target data by first predicting on a particular target instance. And then we're going to add together with the original clean target instance a set of augmentations. In this case, we used RandAug, but you could also use adversarial augmentations. We're going to retrieve a new set of predictions and encode a selective entropy loss. The way that this selective entropy loss works is that we're first going to check for consistency or consensus among the different votes. And this could be any type of voting procedure. We tried a bunch of different ones in the paper, but the key is if the votes are consistent, well, then we can use standard entropy minimization, which means that we're trying to increase the confidence of the model on this particular instance. And if it's inconsistent, we don't want to increase the model's confidence. We want to, in fact, decrease the model's confidence so we maximize entropy. So it's a very simple learning procedure. The key difference is really that instead of treating every instance identically, we're going to make sure that we first judge each instance based off of its notion of reliability under the current learning setting. And we're only going to trust the instances that were deemed to be reliable by having a consistent output across augmentations. And this simple change results in some pretty substantial performance improvements. I'm going to show you a few examples here from the domain adaptation literature, but and in this particular paper, we were explicitly very focused also on trying to understand performance on the categories that are highly susceptible to these divergence criteria, namely the categories that had very few labeled samples in the source data set tend to underperform in the adaptive setting because the model is sort of more vulnerable to the instances where it just didn't have as many training data. But here's one example, this MiniDomainNet data set, which is a popular benchmark in the domain adaptation community. And the performance is measured across 40 classes and averaged here across 12 different shifts, meaning different source to target transformations. And if you were to just take the source model and apply it to the target without doing any adaptation, you would get about 66% on this task. There's a number of different methods, including distribution matching based methods, label shift methods, and some prior work that looks at both the data and label distribution shift, which is what's happening in this particular setting. They work based off of things like a relaxed distribution matching criteria, some self-training, but using only confident pseudo-labels, so using the output predictions of the source model rather than using some sort of a consistency metric. And this more recent method that uses entropy minimization together with contrastive loss, so really using augmentations but learning invariance rather than learning selective optimization. And then finally this work, which is using the selective entropy optimization. In the interest of time, I'm going to actually skip the next couple of results. The paper is on arXiv and has a number of different results if you're interested. One last thing I want to show here is just that when you are optimizing only over a select set of instances rather than over the whole data set equally, one question you might ask is how many instances are you selecting, and especially throughout training, how many are deemed to be reliable or unreliable? And so we looked at that here and found that the number of instances that are selected or included in training does actually increase over time, which was a positive sign. It meant that the model was somehow learning to incorporate more data over time in some sort of an implicit curriculum fashion. And the other question you might ask is just, how reliable is this? It's a very simple consistency checker. It's just data augmentations and passing it through the model and asking how many labels are the same. And we found that it actually had pretty high precision for detecting consistent samples, and that precision remained constant throughout training. Interestingly, detecting incorrect samples by finding samples where all of the output predictions were not the same, that did not have quite as high precision, but it did increase over time, meaning that later on in training, the samples that were still inconsistent were much more likely to be incorrect. So we found that this was reliable enough that it actually improved performance over doing just standard entropy minimization or semi-supervised learning. And it was kind of a promising, very simple, intuitive approach, easy to implement, but offered some pretty substantial gains and really avoided some of the divergence that happens in standard unconstrained entropy minimization. So overall, in this talk, what I was focusing on is a little bit different probably than most of the talks of this workshop, but what I'm focusing on is really trying to drive home the fact that if we want to talk about robustness or reliability of our models overall, and we're thinking about different ways in which we can encode that robustness throughout training, we should be thinking about it at an instance level. There are different images that can be leveraged in more or less a different amount of reliable way, and you might be able to really add more robustness to your model overall if you don't try to ask for the equal amount of robustness across every instance, but rather have it be adaptive per instance. And this is applicable both in a supervised learning context and also in a semi-supervised learning context. So I want to thank some of my group members that weren't already highlighted on the slide. A lot of them had input throughout discussions, and many of them also just contributed a lot overall to this work. And I have hopefully a couple minutes to take any remaining questions that people might have about this line of work. And otherwise, thank you for your attention.
Thanks,
Hi,
Judy, for.
Okay.
Oh.
Okay, sorry.
Go ahead. Yeah, ask your question. Yeah.
Okay, thank you so much for your talk. And I have two questions. The first one is that is the vulnerable extent for an attack method on a data set is measured by the accuracy drop, which means the more it drops, the more vulnerable it is. So, I mean, how can we evaluate the vulnerable extent of an instance? Maybe the probability of the predicting the correct label?
I think that's an interesting question. And if I understand correctly, what you're saying is how can we even define this notion of reliability of an instance? And I think there's a lot of different ways people look into this. And I highlighted a couple, but I don't think we have a definitive answer. So one way in which you could look at it is, of course, you could just look at the output score of the model. That's be like the classic standard thing to do. Of course, many of the models are miscalibrated, especially when you start applying them to out of distribution data. And so that's not usually a great metric, but that is one thing you can do. So if the model has an output score that's pretty low, you could maybe guess that the model isn't very confident on that instance and not trust the output of the model. Another thing you could do is you could, like in the instance adaptive adversarial training work, you could apply a different set of targeted augmentations. In that case, they're going to be adversarial attack augmentations. And you could ask how likely is it that the model changes its predictive output. So this is giving you a sense of how vulnerable that model is to a particular set of fixed attacks. Could also be like this last work in SENTRY where we used not necessarily attacks, just standard augmentations that were assumed to not, they should not be changing these output semantics of the model. And if your model is going to be changing its predictive output in response to those data augmentations, that gives you a sense as well that the model is not necessarily as reliable on that instance.
Well, thank you. And I have the second question is that on the domain adaptation, regarding the trade-off between the robustness and the accuracy, so are there any thoughts or insights about the difference between the video classification and the image classification?
Oh, in terms of robustness?
Yes, and the trade-off between the robustness and the accuracy.
Oh, I'm not sure I follow the question exactly, but so insights about video as opposed to images, like what would change between the two?
Yeah,
yes. I think that's an interesting question. It's not something I've looked into too much, and I think that if you had videos, there's a lot more information that you could leverage in order to try to understand something about the robustness of the model, just explicitly from the video itself. I mean, there's a lot of temporal information. And if you move beyond classification and start thinking about some sort of spatially varying semantic output like segmentation or detection, there's a lot of implicit information just within the image itself. So if you're operating on any of these domains or a multimodal domain, let's say, where there's explicitly a set of paired information, I can imagine you could leverage that in order to get a robustness or reliability output measure.
Well, thank you. Thank you so much.
Okay, any other questions? Okay, then thanks, Judy, for this great presentation. We can then move to the next one. Thank you, Judy.
Thank you.